Well, now we are continuing with the fluid statics. Fluid statics is mainly related to the pressure of liquid or the pressure of atmosphere. And pressure is mainly related to force per unit area. So we have to consider the various types of forces. Then we have to consider in which direction the forces are working, what are the area of cross sections or the areas where the pressure is being exerted. All these facts we have to go through in the fluid statics. Our very first discussion is regarding the condition and the laws of equilibrium of fluid statics. So mainly our discussion will be limited to liquids when they are flowing and when they are stationary. So whenever the liquids are flowing, they have got some definite velocity. The medium is viscous, but in many cases we find that the medium is non-viscous. That is only imagination, assumption. But all the mediums where the fluid is flowing are supposed to be viscous. Then we have to see that in the liquids, there are a lot of molecules, and the distance among the molecules are intermolecular distances, and these are sometimes, and the forces among these molecules are called the van der Waals forces. So van der Waals forces exist among the liquids as well as gases. Now, in the fluid statics, we deal with conditions and the laws of the equilibrium of liquids and gases under the action of external forces, where the fluid mass is stationary. So we will consider the mass of the fluid as stationary. It moves as a rigid body. Fluid is stationary with respect to container. Pressure in the liquids or pressure in the fluid. Our very first discussion is pressure in the fluids. That is, suppose that we take a container, it contains some water or some other liquid. Mainly, we take a general available fluid as water. So in water, suppose that we consider a point well within the fluid, that is water. Then from the surface, we record the height, and pressure will be taken as HdG, that is height from the surface, d density of liquid, and g acceleration due to gravity. These facts we are going to use in the construction of manometer or the barometer, that is the Torricelli's barometer, and their function. Then we come towards the atmospheric pressure, and the atmospheric pressure will be taken as, that is HdG. These facts we are discussing for the pressures in fluid. Consider a point in a fluid in a small area. Now when we speak the small area, the total area is supposed to be S and the small area is supposed to be delta S. The fluid on one side of the area presses the liquid on the other side. Obviously, we are taking either a vertical position or the horizontal position. If we take that is a pipe and some liquid is flowing in it, so in that pipe, the pressure is working from one end to another end, maybe from left to right or from right to left. And if it is a container containing water, it means pressure is working from top towards bottom. However, it can be from bottom towards top also, but that will be the buoyant force. So, the fluid on one side of the area presses the fluid on the other side and vice versa. If F is the force, then pressure at point A is taken as pressure is force by area, but we have taken a small area out of S, that is delta S. So pressure can be written as limit delta S approaching to 0 F over delta S, where delta S is close to 0. It is shown in the figure, that is A point is taken within the fluid and the pressure acting on a small area that is given by limit delta S approaching to 0, F over delta S. Now, an important note is there. For equilibrium of solids, we usually think in terms of the forces, while for the liquids, we think of pressure, since in solids the actual area of the contact is much smaller, but in the liquids the actual area is much larger. So, since in solids the actual area of contact is much smaller than the apparent area of contact between the two surfaces, so the concept of pressure is of no use. But in case of liquids, the actual area of contact is same as the apparent area of contact. It depends upon the shape of the container. For a homogeneous and non-viscous fluid, now before further proceeding, we should say always, when non-viscous fluid we say it is assumption. There is no fluid which is non-viscous. Every fluid is viscous. Homogeneous, uniform. So for uniform, that is homogeneous and non-viscous fluid, pressure at A due to not depend on the orientation, and hence we take pressure at a point. Pressure acts normal to the surface. When we say pressure acts normal to the surface, it means force is operating in the perpendicular direction. So pressure acts normal to the surface, and it is always compressive. That is, molecules come close to each other when the pressure is applied. So it is always compressive in nature, that only its magnitude is required for its complete description. It is a scalar quantity. The SI unit of pressure, or the MKS unit, is taken as Newton per meter square, or it can be conveyed as Pascal. 1 Pascal means 1 Newton per meter square. And when we say 1 atmosphere pressure, so 1 atmosphere pressure will be 1.013 into 10 to the power 5 Pascal. The biggest unit of pressure is bar, and 1 bar is 10 to the power 5 Pascal. So we will summarize it. 1 Pascal means, that is 1 Newton per meter square. 1 atmosphere means 1.013 10 to the power 5 Pascal, and 1 bar is 10 to the power 5 Pascal. Now we come towards the variation of pressure. When we speak variation, variation means either increasing or decreasing. So we are referring to increasing pressures or the decreasing pressures. When the pressure increase and when the pressure decrease, what can be the expectation? For example, we consider an atmosphere. Atmosphere is obviously made up of air molecules, but as we go very high, that is towards the mountains, peak of the mountain, the air pressure will be less, but on the sea level, the pressure will be more. And another thing, that is, when we move from higher point towards the lower points, it is not necessary that pressure everywhere is same. The atmospheric layers have different compositions at the different heights. Therefore, the density of that composition will change also. Now, let us come to the main concept on the variation of pressure. But the main formula which we are going to use will be P is equal to H d G. H means height, d means density, G means acceleration due to gravity. Density we know is mass over volume, and mass will be density into volume. Density will be either represented by d, or sometimes density is represented by rho. So we can take more elaborately d or rho for density. Now, our discussion is like this. Variation of pressure at 2 points in the horizontal plane. Now, what exactly we mean by this? We consider a trough or we consider a container filled with liquid, and within the liquid we consider 2 points. Now, what is the variation in pressure at those 2 points when they are in the same plane, or one of the point is higher and the other point is lower? These facts we have to go through. Consider 2 points A and B in the same horizontal line inside the fluid. Imagine small vertical areas delta SA and delta SB containing points A and B respectively. Now consider the fluid contained in the horizontal cylinder bounded by small areas delta SA and delta SB, so that delta SA and delta SB, if pressure at A and B is PA and PB respectively, then forces along the line AB are PA into delta SA towards right and PB delta SB towards left. Now, when we write this product PA into delta SA or PB into delta SB, we are multiplying pressure and area. Basically, the product of pressure and area will be force. So, when we take this product, we are referring to force indirectly. Now, the next is, as the fluid remains in equilibrium, that is not moving, then in that case, we will equate the two values. PA into delta SA must be equal to PB into delta SB. From this, we cancel off the areas if the areas are same, and PA will be equal to PB. That is, pressure at point A must be equal to pressure at point B. This is the situation when the fluid is in equilibrium. The pressure is same at 2 points in the same horizontal level if the fluid is in equilibrium. So this is shown in the figure. That is, P delta SA must be equal to P B delta SB when the 2 points are taken within the liquid in the same horizontal plane.